Welcome back, and thank you for joining me for part two of this discussion. We left off talking about the gated recurrent unit and how it's very good at looking at time series data due to its internal memory unit. This helps us look at past values in a time series and kind of get an idea of what's going on in the future. So it keeps track of past events in a time series, which is very important when you're thinking about how the human mind works. Past thoughts and actions influence our future actions, so the brain definitely works in this way. So it makes logical sense for us to look at this type of model. You can see we implemented the model here. We used a special version of the GRU unit called the CUD GRU, which is basically the CUDA GRU, and it's basically a graphics card optimized version of the GRU unit. And the idea is that it works much better on a computer that has a graphics card like the Google Colab allows you. They give you a K80, a Tesla K80, so this actually speeds things up quite a bit. So you could see that we define the model up here, and it ends with a typical dense classification, once again using softmax. We'll see this over and over again. We're trying to get 10 classes. And then we once again define the running of the model using splitting into train and test with our targets and source data, and then reshaping. Since we're using sparse categorical cross-entry, we don't really need to use the two-categorical function. Our targets are just integers, 0 through 9, so we could usually use them directly along with the sparse categorical cross-entropy loss function up here, which is a good way to go about it. Because this model was taking a little bit longer to load, I included an option to save the weights and the variable names halfway through so I could pick up where I left off, but this isn't necessary to run. It was just kind of a checkpoint system for myself. So we went ahead and we trained the model, as you can see down here, and we're just going to scroll down here. But it didn't turn out to do as well as we would have thought. And let's get back to the slides here and look at why. So you could see those two figures here that were in the notebook are right over here. You could see the model accuracy is kind of going up and up, and the loss is going down on the training set, but the test set's really not changing. And this indicates that we're getting some overfitting here. This could be due to the model just not being well suited to training on this type of data, or the model not working the way that it's expected. What might be at play here is the EEG data is very highly variable. It varies between between sessions. It varies between locations and just throughout time as well. It's just a highly variable stochastic signal. So maybe GRU is not as good at looking at highly stochastic time series data. Maybe it works better with more structured time series data, like climate data or daily temperature swings or things like that. But we didn't want to completely discard it to start with. We wanted to also look at spectrograms using GRUs as well. The reason is that a spectrogram is technically a time series. You could see here on the x-axis we have time in seconds. The only difference between this and what we see back over here is that this time series is one-dimensional, it's a line, and this time series is two-dimensional. We have the x-axis in seconds, and we also have frequency information encoded on the y-axis here. So we're going to just feed in a two-dimensional time series into the GRU. And we can see that in our notebook down here. We have a second edition of the model here with different input shapes. Basically, we have the number of samples as well as the height of that image, the spectrogram height that's going in here. But besides that, the model is exactly the same as before. We then run the model over here using, again, pretty much the same idea as before, except instead of feeding in the raw data, we're now feeding in the spectrogram values over here. We then reshape things to fit both sizes of the spectrogram. That's what feature size is. It's feature size 0, the x dimension, and feature size 1, the y dimension. And we reshape the train and test data to match that. Besides that, everything else is the same. And we go ahead and we train our model. And you can see the training down here. So as we go into the results of that, also we noticed that we didn't get very good results from that. The accuracy was actually much better on the test set, and it was much better on the training set than the other models. So by feeding in the spectrograms, it did make the model have an easier time with the training, but we didn't really notice much of an improvement with the test set. You could see we're just kind of hovering around here. So it didn't really affect that too much. But I feel like with more parameter tuning, we could actually end up doing much better with this method. So more investigation is needed here. The jury's still out on this, but for now we'll look at some other methods to start with. The third method we wanted to look at was called the UMAT method. This stands for Uniform Manifold Approximation and Projection. It's a way of reducing dimensionality of a dataset, and it could also perform unsupervised clustering and feature extraction. In practice, It could be used for its dimensionality reduction functionality, and that's kind of can be thought of as a nonlinear cousin of PCA and reducing dimensionality. In the clusters it produces, as you can see some examples here down with the fashion MNIST dataset, the cluster it produces look very similar to the t-SNE projections that we've used in class. In fact, UMAP is related to the t-SNE method, although it's not stochastic, meaning that if you feed it in fixed numbers, it will produce the same clusters every time, which is useful from a scientific perspective. It makes the data much more reproducible if you can produce the same plots every time and not have to reinterpret a t-SNE plot that looks different just because it's a different stochastic seed that's been fed into it. So this is actually a very useful feature. One parameter we have to tune here, there's a bunch of hyperparameters, but one of the most important ones is called the n neighbors. The n neighbors determines the number of neighbors that are used to perform the embedding. And you could see by changing the number of neighbors, we could drastically alter the size of, alter the way that the plot looks. Basically, on a high level, this n neighbors parameter tunes UMAP's ability to look for the relative importance of local clustering versus the overall global shape of the data. Because the clusters have things in common with each other, like each point has things in common with each other, as well as the clusters spaced next to each other on the whole. And you can see that over here, this is perfectly illustrated when we add labels to our data. So when we look at our data here, you could see the numbers are labeled by increasing in number, starting on the right and moving over to the left, and the the getting darker color indicates that a higher number in the sequence. So you could see a great representation here of the local structure of the data being preserved. The local like digits are clustered together, as well as the global structure of lower numbers over here and higher numbers over here. So that's kind of I found that very fascinating that worked right out of the box. This is very exciting. So what we could do with these, this is a graphical view of our embedding in 2 dimensions, but embedding can happen in any number of dimensions. So you could use n-dimensional embedding and use those embeddings to train a dense neural net classifier, which is what I did. I figured that we'd have an easier time now that we've done this embedding and already did some pre-clustering of our data. And it turns out this was actually a great way of going about this. We were able to get pretty high accuracy for our model using this pre-embedded and transformed data. So this might be a nice way in the future of looking at highly variable data such as EEG, and to perform this type of transformation and clustering is a good way to kind of look at it. So it's a good discovery going forward with any type of highly stochastic time series data. The fourth unit we looked at was the echo state network. This was looked at. It's a special type of recurrent neural network that uses a block of units that have untrainable weights, and this block of units is called the reservoir. So the reservoir, once again, creates a high-dimensional embedding of the input, which could then be fed onto the classifier. And basically, this reservoir is very sparsely connected, and previous time points in the series tend to influence or echo even after they've passed through that round of training. So the echoes kind of accumulate in this reservoir, which is very sparsely connected, and then future data that you feed through is influenced by the past echoes that are kind of stored in this reservoir. This is kind of the equivalent of the memory unit in the GRU, except a little bit more advanced in a certain way. The advantage of this system is that you don't have to train as many weights as you would with a traditional LSTM or something like that, because all the weights of the reservoir are locked from training. So that's already just locked. They're basically initialized randomly, so you get a bunch of random numbers and they're just kind of locked in place, which is pretty interesting. And the other advantage is that ESNs don't necessarily suffer from the vanishing or exploding gradients problem, which is more of an issue for LSTM and GRU and other like counterparts to that. What ended up happening here, and I'll show you the notebook for this, is that we did everything the same as we did before. These functions should all look familiar, and then I know we're still trimming the data, making sure everything's the same size. We import the library. Basically, this was all taken from a paper, which I found, which was very exciting. I included a link in the report to the paper that you can read it. It's pretty interesting. And there's also a GitHub associated with that paper. So we clone their code into a repository to work with it. We then can fit our data into their framework by assigning our X training and X test sets and our Y training and Y test to their variables, and we could kind of proceed from there to see if we could fit the model. These are other parameters. These are other hyperparameters. This model has a ton of hyperparameters, and it discusses all of them in the paper. but we're not going to get into all of them here. Basically, what happened here is this used a ton of memory, so we had to do it on an EC2 instance, but the performance was not fantastic. Once again, we are feeding in raw EEG trace data, so what I'm thinking here is that the data is once again still too variable for this model to really be useful here. Some amount of filtering or smoothing could help with this, or doing a transformation on the data could help before feeding it into this model. So that could really help it do a little bit better than what we're seeing here. So in conclusion, we tried using convolutional neural networks, we used GRU, we used some UMAP, and we finally finished off with looking at some echo nets, with the most successful being the UMAP followed by neural net classification. We discussed that. The spectrograms were limited due to the inherent issues with using an artificial image with convolutional neural networks, and the GRUs didn't do very well due to the variability in the data, and I think that was the downfall of the ESNs as well. So some more data manipulations will be necessary to make those useful. I really think they can be useful in classifying these time series data, but it really would require some more work manipulating, cleaning, and transforming the data. Some future directions we can have here are there might be different alternatives to ESNs, which perhaps an intentional network might be less sensitive to this noise. It's definitely worth it to look at these different types of networks that might be less sensitive to this highly stochastic signal of the EEG. And as I mentioned before, I think we can really optimize the GRU network, mostly optimizing the data being fed into the network to make it a little bit easier to train on and easier to predict. Perhaps doing different transformations, perhaps normalizing. Another thing that could be work well is a nice median filter or a rolling average filter to smooth out the data or knock out parts of the data that are causing problems. The third thing that might be worth looking at is looking at a type of a Granger causality, which is a system for, it's basically a statistical method that determines how well one signal predicts future values of another signal. And that's good for multi-channel data to tell you where different data sources are coming from and what is influencing what. It really takes into account how different signals interact with each other, because when it comes down to it, we're recording millions of neurons in the brain at the same time, all firing at once. So there's definitely some neurons having inputs into other neurons and having effects on the output that we're seeing. We're only seeing the final output. We're not seeing any of the hidden stages, like the hidden layers of the brain. So the Granger causality is a statistical tool that kind of lets us dig into that. So thank you so much for listening to my talk here. We'll upload these videos so that they could be viewed. The notebooks will be available too, so everyone can check them out. You can see all the notebooks are here. All the data in the notebook is here as well. Some additional goodies in the notebook, you could see I did a test to see what the best neighbor embedding would be. You could see we start at 5, there's not much embedding in UMAP, and then we get to 10, and once we're up to 25, we're beginning to see our clusters, and by the time we get to 100, we have nicely separated clusters. So you could really see in the notebook how this hyperparameter of n neighbors really affects UMAP. What I also did in this notebook was I fit the other data set. I mentioned in the beginning the emotive data set, and you could see here's the emotive unit here with its multiple electrodes, and here's where the electrodes go in the head. So I wanted to see if this data would be, would help, looking at a larger data set with more electrodes to see if that could help us with any of our models. It helped a little bit, but it was not super useful. Pretty much the data set was a little too large and unwieldy, so I had to perform some shortcuts. Basically here I'm looking at the O electrodes, which are at the back of the head, the occipital lobes. Those are the areas implicated in visual processing in the brain. So I figured it would make sense to look at those. The visual signal is going to come into the brain there and then be propagated to the rest of the cortex. So I figured if I could classify and pick up a difference at these 2 electrodes here, I'd be in good luck for looking at other regions in the brain. So that was a decision I made to try to make the data set a little bit more manageable in size. And we trained the same models as before, the GRU model and the UMAP model. It performed very similarly in the UMAP model. You could see the results of that down here. And the accuracy is very similar as well. So at this point, I'll just wrap up, not take too much more of your time. Thank you so much for listening to my report, and happy hunting.